Okay, welcome back. We are now starting a new chapter on Perelman's contribution to Ricci flow, which is a basic new interaction between concepts from Riemannian geometry, Ricci curvature in particular, and the heat equation, reaching also into stochastics and having many applications, say optimal transport. So it's a major new discovery, and I would like to begin by motivating that. So, Perelman's W functional and Ricci flow and the application to non-collapsing the motivation is that we want to, in the context of this course, study Ricci flow under less restrictive assumptions. Ricci flow under less restrictive assumptions in higher dimensions. The two-dimensional case we treated completely. So in particular, we don't want to assume positive curvature and some pinching assumption like last time. And in particular, we want to understand more in the case n equals 3. We want to study n equals 3 without curvature assumptions. And this is, of course, what leads in the long run to Hamilton's and Perelman's proof of the Poincaré conjecture. We will not get that far in this lecture, and even the geometrization conjecture of Thurston. I will say a little bit to that later on. Now, where are we? What is the state of affairs that we have reached in this course? What did we accomplish so far? Well, we showed in any dimensions that we have a solution for smooth initial data a solution on some maximal time interval and this maximal time interval may be finite or may be infinite, and we've seen that if the time interval is finite, the maximal time interval, then this can only happen if the curvature becomes unbound. The modulus of the Riemann tensor is unbounded for t tending to t max. And I'm talking here about the case where we have compact initial data without boundary, smooth initial data on a closed Riemannian manifold. Now, if we had the case n equals 3, we know a lot more. First of all, we have the famous initial result by Richard Hamilton. If the Ricci curvature of the initial metric is positive, then this is preserved, and we get the pinching estimate. And after rescaling, and we can simply rescale by volume to keep the volume constant, we get convergence to a spherical space form. To some quotient of S3 by a group of isometries acting free. Now, we knew some more. We had this one estimate by Hamilton Ivy, which is significant because, oh, by the way, if the Ricci curvature is not positive, other singularities can happen. So, if Ricci G0 is not non-negative, then you get other singularities. This is nothing I prove, but it's intuitively clear, and there are proofs in the literature. It's not so important that we prove that. I think it's pretty clear that you have singularities which, in terms of picture, look like this. You can get initial data which look like this, and then here there is some S2 of a very small radius r, and if you make this neck long, then this S2, because it has strictly positive Gauss curvature, we know this S2 will shrink, and if you make this configuration such that the neck is long and thin, then you end up with a solution which develops sort of a very thin neck here, and eventually something goes wrong, and we can imagine that maybe when we look at this under the microscope and rescale, in this case it may look like a shrinking cylinder, if more and more like a shrinking cylinder, if we look under the microscope. In other words, if we do this rescaling procedure that I mentioned in one of the previous lectures. So this kind of thing can happen. So in this case, the volume rescaling will not help us. We have to do something else. And I also mentioned that there may be a situation where the bubble here is not so nice symmetric, but there's one big bubble and a small bubble here. And then you have again this S2 sitting in here, and this will shrink very slowly, but this shrink faster. If we adjust the size of this bubble compared to that bubble exactly right, then it will also not slip through and get into the positive Ricci curvature case, but it gets stuck. So we get somewhere on an object like this, and this is another singularity that looks very different. And if you look at this under the microscope, you might anticipate that you get some surface which looks like a bowl, and only here attaches to a cylinder that looks like this cylinder here at a different scale. So we anticipate this kind of singular behavior to occur. We didn't prove any of these pictures, but what we did prove is the following. We proved for n equals 3 the Hamilton-Ivy estimate. Namely, we proved that the negative part of the sectional curvature is small compared to the scalar curvature if the curvature blows up. So negative part of the sectional curvatures becomes small and this was a very precise technical estimate involving the logarithm of the scalar curvature compared to R as R tends to plus infinity. And this led us to show that any rescaling in this three-dimensional case, any smooth rescaling, has non-negative sectional curvature. So this we proved, so this Hamilton-Ivy estimate we proved rigorously from the maximum principle. And in these pictures this means, despite not having even positive Ricci curvature in this example, if we scale we get the cylinder here in this example, which is non-negative sectional curvature, or we get something which looks like this bowl and would have strictly positive sectional curvature. Now, there's one thing I didn't prove, and I don't have time in this course. I mentioned there is this strong version of the parabolic maximum principle for tensors. And that strong version of the maximum principle for tensors tells us that this non-negativity here exactly can distinguish between this case and that case. So this is something I'm just telling you, that from the strong parabolic maximum principle for tensors, I did prove the weak one for tensors, but if you take the strong parabolic maximum principle for tensors, which is proven in the reference I gave you by Richard Hamilton on four manifolds with positive curvature operator, we found the proof. So if there's strong parabolic maximum principle, it says that if on this limit either on the rescaling, which is a three-manifold with a metric, let's call it G infinity, because it's a rescaling. This rescaling will be on some time interval that reaches all the way to minus infinity, as I explained. On such a rescaling, we have non-negative sectional curvature, and then we have just, by the strong maximum principle, two possibilities. Either all sectional curvatures, all pairs ij are strictly positive, that would be this example here, or alternatively, the only other possibility is that one sectional curvature is zero everywhere. And in that case, it turns out you have, in fact, two sectional curvatures equal to zero, and the thing splits into a two-dimensional surface and R. Or the three-dimensional solution that we get is in fact a two-dimensional solution cross R, where G tilde is a solution of Ricci flow. Okay? So either we are in a situation where this thing has strictly positive sectional curvature, the rescaling, or we get something which is two-dimensional. Now, if we just studied two-dimensional Ricci flow, now, and we showed that if we have a closed surface with positive, this two-dimensional metric has, of course, positive Gauss curvature. So G of G tilde is strictly positive because we rescale it in such a way that one of the sectional curvatures is positive, so the Gauss curvature is positive. Now, it's a closed surface with positive Gauss curvature. We just proved in the previous lecture that that would converge to a round sphere, and it's not so hard to see that in this case, if you're in this case, and this surface sigma 2, which exists on such a long time interval, actually this must be around two sphere, just around shrinking cylinder. So we have exactly this example. The problem is that this thing may not be a compact two-dimensional surface. And the problem is, of course, also that in this rescaling procedure we needed a compactness theorem. So there is two major open problems to further progress in three-dimensional Ricci flow at this stage of our knowledge. Let me summarize these two major open problems. So, major problems at this stage of our knowledge. So the first one is we need a compactness theorem to make this rescaling procedure rigorous. I just told you how you rescale, but I didn't prove how you get a limit. So and for this compactness theorem, so for this we need a lower bound on the injectivity radius. In the one theorem we proved that we had the positive curvature and the pitching estimate. We got around the problem by using Klingenberg's lemma, which is a special situation in the positive curvature case. Now we don't want to assume positive curvature, we don't have Klingenberg's lemma. Therefore, we have to find some other way to get a lower bound on the injectivity radius. The second problem is that even if we can carry out the rescaling, then we get a limit. It could be that this two-dimensional surface is not closed. So if sigma 2 with this metric G tilde of T on minus infinity less than T up to some capital T, if this is non-compact, the following example might be possible. I showed you this two-dimensional example. There is this solution of Ricci flow, which actually was a Ricci soliton, which looked like this. So sigma 2 diffeomorphic to R2, and the metric ds squared on this surface given just by dx squared plus dy squared divided by 1 plus x squared plus y squared. Which means that for large xy, it looks like a cylinder, and here it has curvature 1 at the tip. And with this metric, if we start a Ricci flow on that, the shape doesn't change, it's just a soliton solution where just the coordinate system changes. Was one of the examples where the flow is just a flow of diffeomorphisms on the surface, so you change the coordinate, the same metric reoccurs in a different coordinate system. Now, this, if you think this is the two-dimensional surface, this means since the three-dimensional thing is cross R, it means that the three-dimensional manifold sort of looks like a sheet of S1s. Right? There's all these S1s, and then we have a two-dimensional sheet of this one-dimensional surface. Now, this, if something like that appears as the rescaling of a singularity, it means that in this singularity we might have a neck which is sort of deteriorating rather than having a nice round S2 cross-section. It means that in this neck somehow the thing looks like a pancake, like one of these funny things with the S2 sort of deteriorating into a cigar. Hamilton called this the cigar solution. The physicists who studied this from a completely different perspective, they call it the Witten black hole. But that's just an aside. So, and this is of course a disaster because it would prevent us to do anything further with the Ricci flow. We have to get rid of this picture because it would prevent us from proving the Poincaré conjecture. Why is that? Let me make some comments on what the long-term strategy is in the three-dimensional case. So this has to be ruled out. Because otherwise we have degenerate cross sections of neck singularities rather than round singularities. And this would destroy the strategy towards the Poincaré conjecture. Let me say a few words, but despite us not being able to carry it out, just to motivate. What is the strategy? As you know, the Poincaré conjecture is saying that if M3 is closed three manifold, smooth, and simple connected, then M3 is diffeomorphic to S3. So the idea is starting with Hamilton, start with any metric on M3, say G0, and evolve by Ricci flow. Now, if we ever get, at some stage, we would have to get to a singularity. So, so one step that one has to show is show that a singularity happens in finite time. That's a problem in itself. Because we know in a two-dimensional case, say on a torus or on a negatively curved manifold, we have a solution for an infinite time. So to show that you have a singularity in finite time is a separate piece of work, which I'm not going to talk about. So to show that you have a singularity in finite time, then we know the curvature blows up. So look at the singularity. Consider the singular behavior at t tends to t max. If at some stage we find positive Ricci curvature everywhere, then we are done, because we know after that it will converge to a round sphere after we scale. So if at some point time t naught less than t max, the Ricci curvature of g of t naught is positive, then we are done. Because then we know from then on, we can just rescale by the volume, converges to a metric of constant sectional curvature, and that must be S3 or S3 divided by some quotient. But the only one of those that is simply connected is S3 itself, so we are done, because then everything was smooth, everything was diffeomorphism. If not, then we must have had a different singularity. So if not, find a different singularity. You rescale that singularity, and look, what do you get? If we get this, then it was one of these singularities, or one of these singularities where the cylinder is sort of attached here, and you find this rescale. So if you get that singularity, you cannot proceed further. But if this is ruled out, so if the cigar cannot occur, if we manage to rule out the cigar, then these are the only two types of singularities. Show that picture A or picture B are the only possibilities. A and B, only possibilities. And then what you do what they call surgery. You cut this neck and you cut off this horn. So then cut necks or cut horn. Cutting means you attach something smooth with much less curvature, some caps. You heal the patient by doing surgery, and then you continue the flow until there's only until you can show that the only pieces that remain are such pieces. Because the thing was simply connected, this thing here will create two disjoint components. You do the work on each of them. And here, since it's simply connected, this does not change the topology at all. So you keep going and you prove, this is the hard work, you prove that this surgery has to be done only finitely often. So you show that after finitely many such surgery operations, where you get rid of these kind of singularities, you end up with pieces that either you know are spheres or where such singularities are no longer possible. So continue now after finitely many steps, show that only spheres are left. So you show that after finitely many such singularities and surgeries, you end up with finitely many S strings. But if in the end you have finitely many S strings, and the only topological change that ever happened was the inverse of a connected sum, then the original thing must have been diffeomorphic to a connected sum of those finitely many spheres. But the connected sum of a sphere with a sphere is just a sphere again. Therefore, the original object must have been an S3. And that proves the Poincare conjecture. That's the strategy. Now, it's absolutely crucial to be able to do this surgery, to do this thing in a quantitative, careful way, so that we have so much control that we don't have to do infinitely many of them. If we have to do infinitely many of them, we are lost. So that we have to control this procedure quantitatively, so carefully, that we can prove there's only finitely many. And for that quantitative control, it is absolutely necessary that the cross-section of these necks is round and that this picture here is ruled out. So this was around starting 95, Richard Hamilton had reached sort of this stage of affairs, and he was trying to rule this out. And this was not possible to rule out until Perelman's work and the paper of Perelman that came out in 2003. Now, how can one possibly rule out this picture? What is what distinguishes this picture from the other singularity, from this horn or from the round neck pitch from S2 cross R? What could be a way analytically to rule this out? What makes this special? What is wrong with this cigar? How can we somehow prove it cannot occur? Well, one thing you notice geometrically is that on this cigar you can use a tiny, tiny circle to bound a huge amount of area. In other words, this cigar has a terrible isoperimetric behavior. So it has bad isoperimetric behavior. Small circles bound huge area, which means that this is on the two-dimensional surface, which means that on the three-dimensional surface, which is sigma 2 cross r, you can use small areas, two-dimensional area, to bound a huge amount of three-dimensional volume. Small area can bound huge 3D volume. So in other words, this thing has a very, very bad isoperimetric constant. So one way to possibly attack this would be to prove that there is a good isoperimetric constant, or some isoperimetric constant that was true everywhere initially is preserved under the flow. The other thing that's wrong with it, without talking about the isoperimetric inequality explicitly, is what they call collapsing. We have a collapsing behavior here. What does collapsing mean? Well, usually in a three-dimensional space, you expect that the ball of radius r has volume comparable to r cubed. Now, if the curvature is huge, in the positive curvature, that's one thing we proved in the pinching theorem. And we had to use Klingeberg's lemma to that. So there's a problem that if there's a huge fundamental group, this could be wrong, or if there is a lot of zero curvature. So this seems to be exactly the case here, because on this cigar, the Gauss curvature is tending to zero, but there is a very small injectivity radius. The circle here is very limited length. Say if this is curvature at 1, then these circles have approximately length 2 pi or a little bit more, I don't remember. And but the curvature is essentially 0. So on this stream manifold, on this M3G, there are balls of radius r, so we have br around some pi or some p. So take some big radius r here with the volume of this ball around P, roughly it's like 2 flat directions and 1 direction rolled up. Looks essentially like a cylindrical metric, so it's something like 2 pi coming from the circle, and then some constant times r squared, but not r cubed, just r squared. While the curvature, if I take this point out, direction s, and you compute the curvature in this direction, you see that the Gauss curvature here is between 0 and some constant, I think it looks like e to the minus s. In other words, the Gauss curvature is very, very small, the radius here can be huge, can be of size S, but you don't get the volume of order R cubed. So this is what's called collapsing. On the other hand, on S2 of radius R cross R, in other words, on our cylinder, here, this is the S2, and here is S. Then you have the, if this is the radius here, if this radius is R, then you have the Riemann tensor is bounded by, say, R to the minus 2. And then if the if you then look at the volume of a ball of some radius rho, which is less than this R, and then you find some constant depending on dimension 3 times rho cubed for all rho less than R. So this behavior that if you have the Riemann tensor bounded at this scale, that then for all smaller scales the volume grows like it should with the right power of rho. This is called non-collapsing. And it's the thing that distinguishes the S2 cross R from the cigar. So there's two ways to look at the way that the two possible rescalings of the singularity differ in a geometric way. The cigar has a very bad isoperimetric behavior. Here you have a reasonable isoperimetric behavior, and you have this collapsing behavior that despite the curvature being small, you are still not close to the three-dimensional behavior, which is not the case. Right. So we can either rule out to rule out the cigar, we have to either rule out bad isoperimetric behavior, or we have to rule out the collapsing. And I guess this is a good time to have a break.